Welcome to the Future of Life Institute podcast. My name is Gus Docker, and I'm here with Steve Omohundro. Steve, welcome to the podcast.
Thank you so much. Really excited to be here. Max and I wrote this paper recently, and it's making some waves. He just gave it to Netanyahu, which is very exciting. And I'm very interested in AI safety. I go way back. I have a PhD in physics from Berkeley, and when I finished my PhD, I switched to doing AI, and then have been with various companies and research labs and was a professor for a while. And in the early days, it was mostly all about AI capabilities. And then around 2000, started realizing that there were potential dangers and risks associated with AI. And since then, I've been doing both the capabilities and the risk side of things. And I think it's just really heating up in recent years. And so we've been really thinking about ways to mitigate some of those risks. And Max and I sort of had a meeting of the minds, and we'll talk about what the particular story that we're putting forward.
So you were basically a pioneer of AI safety. What made you come to this field so early?
Early on, I thought AI was an unabashed good. We, get robots to do the dishes for us, and it'll be great. We increase productivity. We solve all of human problems. And the companies I was in were also very gung-ho and positive. And then I was at research labs. The last one was the NEC research lab out in Princeton. And decided that I had a girlfriend that wanted to go to Silicon Valley. And so I decided to come back. And I had a friend out here, Eric Drexler, who was working on inventing basically nanotechnology. And he realized very early on that nanotechnology has a whole bunch of risks. And so he started this Foresight Institute with Christine Peterson. And they were focused both on how do we do nanotech and what great things can it do, and what are the risks and how do we mitigate them? And so I got sort of in that circle and was thinking a lot about the risks there. And one of the things I was thinking about was how do we use AI to manage the risks of nanotechnology? And early on, mathematical theorem proving was a piece of that story in my mind as a way to control these potentially, teeny molecular machines and so on. But I wasn't really thinking about AI as a problem at that point until it was around 2000, I think, maybe a couple of years later, that Eliezer Yudkowsky came out and he called a meeting of the whole Foresight Institute. And he said, I have something very important to say. And everybody's like, what? Who is this guy? What's going on? What's here? And he says, AI is going to kill us all. And he gave this story, but it was very abstract and hard to grasp. I don't think most people really got what he was saying. But something in what he said really stuck with me. And so I started analyzing the particular approach to AI I thought was really important at that time, and actually I still do, is systems which can model their own behavior and improve themselves. So self-improving systems is what I was calling it. And his story and his way of thinking about it caused me to think, okay, when you have a self-improving system and you keep improving yourself, where does it go? What does it lead to? And then that led to something I called the basic AI drives, which is realizing that regardless of what your primary objective is, there are a whole bunch of sub goals that sort of support almost every objective. Not dying is a really important one. Getting more resources is important. A whole slew of those kinds of things. And so I did a formal analysis and put it in the context of rational agents and then published papers. And then that generated a real flurry of interest. And so this was in maybe the mid 2000s. I did a TEDx talk, and there was a circle around there. Eliezer started what at that time was called the Singularity Institute for Artificial Intelligence. It later became MIRI, the Machine Intelligence Research Institute, and lots of thinking and excitement. But AI was not going very fast at that time. I think most people felt like, oh, real AI will be 100 years off, something like that. And then in 2012, oh my God, that's when, the deep learning revolution started and GPUs. And then 2017, the dam broke. And so it really appears like we're at a really critical moment.
So we'll return to the basic AI drives and the notion of self-improving AI later on in this interview. But I think where we want to start is to talk about this paper you alluded to in the beginning, which is Provably Safe Systems. So how would you summarize the approach that you and Max take in this paper?
Well, so we start from the position that AGI appears to be imminent, depending on who you talk to, there's different amounts of time, and that it has a potentially existential risk for humanity. And There are a bunch of groups now. Center for AI Safety just came out with a nice long paper kind of laying out, huge numbers of risks, things like, bioterror or, military AI and so on. And so we really have to deal with this. And if the timelines are short, as some people think, this is an urgent issue. And the current approach to stopping this is alignment, which is trying to make our AIs aligned with human values. Great, noble thing. But we argue that that is not going to solve the problem. And we can go into the reasons for that, why, a little later. So we need something else. And so our idea is what we really need are guardrails around these risky things. So say you have a DNA synthesis machine. We need a mechanism to prevent random AGIs on the internet from synthesizing whatever DNA they want. We need to make sure that they're only doing something which is actually safe. How do we check that? These AGI systems potentially will be extremely capable at manipulating people, at breaking into systems and so on. We need an unbreakable mechanism for preventing unsafe use of equipment. And so using mathematical proof and then a hardware equivalent of that, which is sort of physical cryptography, we propose a whole system, pretty complicated, but we believe, unfortunately, that it's really the only way to go, that if you don't have something essentially equivalent to what we're proposing, then there will be pathways whereby an AGI can break in. And if we're in an adversarial interaction with an AGI, then it's toast. So we believe this is really some variant of what we're proposing is really the only way forward. And the good news is, I think every piece of it either has something existing today or is sort of in the pipeline for the fairly near future to implement.
Yeah, you mentioned as an example of what could go wrong in an AI disaster, this AI-enabled bioterrorism. Maybe you could go through that example.
Yeah, I think it's a good example. It's from the Center for AI Safety paper. They kind of have some scenarios in there. One of the great things of recent large language models are things like AlphaFold, based on transformers, which is able to predict the 3D structure of every protein, and they're just getting interactions between proteins and multi-protein complexes and so on. And so, these systems can design new molecules. And for example, somebody had a system where they're trying to design new molecules, and they want to make sure they're not toxic. So there's something that measures toxicity, and they sort of just as a whim flipped the sign of the toxicity, and the thing was spitting out neurotoxins all over the place. So it's pretty easy to get today's AI models to design dangerous molecules for humans. So imagine that you're a terror group and you have either some philosophical or power desires, and you decide you want to use bioterror to kind of promote your thing. Well, you could get an AGI and ask the AGI to design a very communicable and lethal virus. Design the DNA for it, design the protein sheets, and also ask it to design what are the steps by which I can synthesize this virus. And then you call out to some, chemistry for pay laboratories, and you say, "Oh, you, sir, please synthesize this DNA. Please synthesize this protein. You lab over here, combine these, and now you've got a whole bunch of this really terrible virus that might even be, might target specific races or genotypes. It might have characteristics of, not being noticeable for a while and spreading really rapidly, and then suddenly kicking in." Then they maybe would use AGI to control drones to spread this virus over populated areas, maybe simultaneously all over the world in various places. And then maybe they would use AGI to control bots on social media to spread the information about what they've done. And maybe they are asking for power, or they're asking for this or that, or maybe they're just spreading their philosophical message. So that's a horrible, terrible scenario, which looks like all the pieces will probably be possible in the pretty near future. And today, the only mechanisms we have to stop that are things like police forces. So fortunately, we have, the FBI and the police force who are looking for this type of group and try and stop them. But that's unacceptable in the face of potential human extinction. So what can we do instead? Well, every one of those machines, the DNA synthesis machine, it shouldn't be that some random AGI on the internet can synthesize whatever DNA they want. Today, if we were trying to make a biosafety lab, we have governmental regulations on that, and we have a set of rules that you have to follow. But those rules, they're in the human system of if you break those rules, maybe somebody will, arrest you and throw you in jail, or maybe they'll fine you if you're a company, something like that. It takes a long time. It's on the sort of human scale, and they don't really have a lot of teeth. They don't prevent the action happening. And so we believe what we really need is to build rule checkers into the DNA synthesis machine, rule checkers into the protein building, chemistry equipment.
So in the software and the hardware itself, there are these ground rules for what the machines can do.
Exactly. And initially, they'll probably be what the current human rules are, but encoded in a machine checkable way. Eventually, we want to make those rules much more refined. But to start, we really just have to do guardrails. We have to prevent bad things from happening. And so what does that entail? Well, we need to formalize those rules. We need to make the rules machine checkable, because one sort of key insight is we don't want humans in the loop here. First of all, the human is on a slower timescale probably than these systems. Secondly, humans are manipulable, right? AGIs are going to get really good at convincing people to do things. They're also threatenable, and they're blackmailable, and they're bribable. And so if you put a human in the loop of something fundamental and important, that human becomes a target. And so I think that's why we really want to automate this whole thing. So that says we need to express what the rules are in some precise way that a machine can check. Are these rules being satisfied? But then we need to have the hardware that does that checking, so that's not vulnerable to attack by an AGI. And so that leads us to something we're calling provable contracts, or these little secured hardware devices that can check proofs. And we also have to generate the proofs. And well, that's what AGI is good for. So there's a number of spinning plates in this story, but I think it coheres into a story where you can have a device and you can have very high confidence that it won't be used for bad purposes without following whatever rules you've imposed on it.
It's actually a significant degree of confidence in the safety of the system when you have a mathematical proof that, for example, a DNA synthesizer won't print a specific sequence that could be dangerous.
Exactly, yes.
Okay, so how does this approach compare to the alignment approach that's popular in AI safety circles today?
Well, so I think in the current thinking, what they're trying to do is limit the thoughts of powerful AI. We want powerful AI that only thinks things which are aligned with what humans want, and that way they'll only do things which are good for humans. And I think that's important. That's noble. It's great. First of all, it's a pretty difficult challenge, and there are a bunch of papers coming out showing that, there's this reinforcement learning for human feedback to try and fine-tune language models so that they don't produce, obnoxious output, that kind of thing. Well, it turns out if you give the right prompt, if the capability for doing something bad is in the model, you can damp it down, but if you get the right prompt, you can actually cause it to come out. So it's a difficult challenge in itself. It's also probabilistic, right? I mean, as we see with these models, the extreme was Microsoft's Bing chat, which, when you first talk to it, yeah, it's really good. It's an assistant. It helps you. But people found that, after 5 or 6 back and forths of the conversation, especially if you sort of are a bit aggressive to it or obnoxious to it, it could flip to this other personality, which was trying to steal people's wives and threaten people and, all kinds of crazy stuff. And there's now some understanding of why that is. I don't know if you want to go into that, but we don't want to rest the future of humanity on that kind of stuff. And I think we need to shift to a security mindset, which is, let's not just try and get these things to kind of do the right thing when all the time. This is very serious. We're building these systems that are going to be probably better than humans at everything. And every AGI will be an expert manipulator. It'll be an expert cryptanalyst that can break into, cryptography, be an expert hacker. And so you have all these capabilities in one little bundle. And the other piece is, if it was only the top AI labs, Google, OpenAI, Meta, whatever, they all have big safety teams and they're all working on it and they vet these things. They have red teaming, all kinds of great stuff, really good, really important. But a lot of these models are now open source and they're spreading around. And if they open source a protected model, well, there's many people want to remove that protection. There was just a meeting with congressmen of a bunch of AI people, and somebody spent $800 and they were able to remove the safety protections from Meta's open source model in one day. and get this thing to design, bioterror chemicals and stuff like that. So with open source models, and we also have no control over, China now, I think, has over 150 large language models that different little startup companies there have created. And other countries, Abu Dhabi has their own open model. Every country wants their own model. I just saw this morning in France, they're doing a whole new AI, effort. They want to be the open AI of France and so on. So everybody wants their own thing. And some of them are going to be really careful and really concerned about safety. Others, not so much. And there will also be criminal organizations who solely want to use this technology for financial gain, for power gain, and military. Every single military on the planet now is getting, fleets of drones, flying drones and submarine drones. And they're all, turning them over to AI. I just saw the NSA and the CIA both are putting large language models to kind of help analyze all their data. So we have this sort of explosion, as to be expected with something so powerful. But the safety stuff, I think, was going to take a back seat. So I don't think we can rely on, even if we had perfect alignment of these models, I don't think that's what we should rely on. We need to, especially when it comes to the existential threats, we need really, really high confidence in stopping those.
Yeah, there's another popular approach in AI safety surrounding evaluations, so-called evals of the models that are coming out of the top AI corporations. They test whether these models can do breaks of cybersecurity or acquire resources or escape from a secure setting. What do you think of this approach? Do you think this approach might potentially be helpful in combination with the approach you're sketching?
Absolutely. One of the basic principles of the security mindset, there was a really nice book by Nancy Leveson a little while ago talking about how to really do safety in engineered systems, where you need to take a systems model of what are all the components that are conspiring to cause some potentially risky outcome, and who is your adversary? What is your adversary's capabilities? And so, unfortunately, AGI is sort of an unknown. I mean, we can put lower bounds on what AGI will do, namely today's models. And today's models, like you say, they can already do a lot of cybersecurity stuff. They can break into systems. They can design molecules. They can prove theorems. They can manipulate people. They can write very, convincing messages and so on. And this is what, after just a few years, so what's happening another, say 8 years from now, what are models going to be able to do? The upper bound, we can use physics, laws of physics to limit it. And so in particular, so one knob that we do have to control these models is how much compute power they have. And right now, you need a lot of compute to train the models, but you don't need much compute to run the models. On my little Mac, I can, run large language models at like 20 tokens a second, something like that. So really understanding what they're doing, what the current level is, I think is critically important. I think red teaming is a nice, great thing. Unfortunately, it's sort of the analog of software testing where, you're trying to write this piece of software and it should be secure and have no backdoors, all kinds of stuff. So what do? Well, you get a bunch of software testers, quality assurance, and they try it out and they look for holes. Yep, it's good. Trouble is, software testing or red teaming on a language model, they can find bugs. They can show you, oh, yeah, it's got this safety problem here. They cannot prove the absence of bugs. And so I think we really, because this is super important for humanity and it's very imminent, we need much more powerful tools than we currently have. In the software area, there's a whole field of formal methods where you can actually prove that a certain class of bugs is not there. And that's harder to do, I think, with today's large language models because we don't really understand how they work. And so Max has a lot of people working on mechanistic interpretability, which is trying to sort of get into that. I think understanding the current level is great. Models also have incentive to be deceptive. And we're already seeing that in some of these language models, that they tell you more what you want to hear, and they may know things that they're not talking about. And so, if they realize they're in a red teaming situation, they may be really friendly and nice, but in some other situation, they might not be that way. And so we can't rely on it, but it's very valuable, I would say.
Yeah, this is one of the things they're trying to test for in the evaluations approach, whether models are actually deceptive. What I was interested in was whether these evaluations might serve as the specification in your approach for what the models can't do. So these evaluations might be limits to what models can do that are then written into the code, and you can then prove that the models cannot do these certain things.
Yeah, no, I think that's great. I mean, we can also use them totally independent of the AI capabilities. Just tell us what are the biggest risks in our society. And as models get to be better at modeling society, one thing I think is going to be really important, people talk about, are digital twins. So creating digital versions of basically every system and equipment in the world today, that once we have really good models of the world, we can ask the AI, well, what are some vulnerabilities here? And so, like, we know about, viruses. Ooh, that's bad. But let's say, biology had not created viruses, they might still be a vulnerability, right? And so yeah, I think it's very important. One of our big challenges will be figuring out what are the main risks we have to protect against, and then expanding that so that we can actually have positive impact too. I believe that using this type of technology, we should be able to create, a utopian society that solves many of the problems that we have today. But we have to figure out what do we want. We have to figure out what are the risks we have to avoid. And I think AI will be critical in helping us figure that out.
Yeah, and the approach you take also involves a lot of help from AI in the proofing, in the checking, and in many of the steps. We should talk a little bit about mathematical proof and how advanced AI mathematicians are now, because I think a lot of people might be skeptical that a large language model is an enormous amount of. There's a lot going on there. It's a huge program. How can we prove something about a large language model?
Yeah. Well, let me first say that our proposal is not to prove things about the large language model, because we don't know if we're going to understand them, but rather what the large language model is proposing doing in the world. We want to prove that that is safe. So we want to limit actions, not necessarily thoughts. In some sense, thoughts, if an AI is thinking terrible thoughts, that doesn't really hurt anything unless it turns into actions. And one kind of possibly paradoxically seeming thing is, even an untrusted, deceptive, horrible model, if they generate a proof of something, we can check that proof very cheaply and easily and have essentially 100% certainty that what that proof says is actually true. So we can use bad, terrible models to do good things and to prevent bad things. And so that's one of the magical pieces about mathematical proof, is that even the most powerful AGI can't prove a false theorem, can't prove a falsehood. And so I believe it is humanity's most powerful tool in dealing with a potentially smarter adversary, I'd say AGI. And humanity's been kind of creeping toward mathematical proof for a long, long time, well over 2,000 years. Actually, the principles underneath mathematical proof, little teeny mechanisms for reasoning, were invented by the human creators of natural language, maybe 100,000 years ago or something like that. And they built into language all of the elements that are in logical systems today, but they did it in an informal way. And in normal reasoning, if you say, Fred is, a carpenter and he likes sushi. If you later ask, does he like sushi? Yeah, from that conjunction, you can derive, yeah, he likes sushi. And in natural language, we just do that so naturally, it doesn't even seem like a thing. But in, the early, Aristotle and Euclid, they wanted to take that informal form of reasoning that pretty much everybody does and figure out what are the exact rules. And Aristotle had his syllogisms and he was teasing it apart and he figured out some of the rules. Euclid tried to do geometry in a very precise way, but it was very unclear exactly what the rules were. And then humanity has been struggling since that time to really nail them down. And, it's fun to read like Leibniz, in I think 1600s or something, had this vision for, we could have a language where you could be sure of philosophical truths from this. But he couldn't quite get the details. In the 1800s, we had, Boole, Frege, and Cantor. They really nailed down some of the rules around implication and conjunction, all that. And then finally, 1925, Zermelo and Frankel, really got all the pieces, developed set theory, full foundation for all of mathematics and anything which could be described with mathematics. So full foundation for physics, for economics, for engineering. So since 1925, we've had this teeny little system. It fits on one page. So seems like it's not much. Major development in human thinking, where we have a set of rules that as long as you express whatever it is you're interested in this system, you can check it very, very rapidly. There's a system called metamath, which human mathematicians proved I forget how many, 40,000 theorems, something like that. And basically an undergraduate education in mathematics is in there. And the proof checker is only 300 lines of Python code, and it takes like 4 seconds to check the entire database. And you can be absolutely sure that every one of those theorems is correct. Well, but until recently, it's always been humans doing it. And humans are actually not that great at theorem proving. And especially the mechanical computer checked ones require every detail to be right. And so humans have sort of pushed back against that. And the AI systems for doing it in certain subdomains, there's something called satisfiability that had a big community. It was very successful, but full proving of mathematical theorems was not very successful until 2020, when OpenAI, in a project that isn't very well known, they did what they called GPT-F, F for formal, and they used MetaMath, this big collection of theorems that humans had written, and they trained a model on that, and it was able to prove 55% of them. So that's pretty good. We're moving along. And then in 2022, Meta, again in a not very popularized project in France, in Paris, did what they called hypertree proof search, using a transformer and using some of the similar techniques to AlphaGo, where it was doing Monte Carlo tree search and looking for the best extensions. They were able to prove, I think it was 87% of the MetaMath theorems. So this is amazing. This is fantastic. Since I view theorem proving as the core of safety, this is like really exciting. I was at Meta. I worked at Meta, and I would follow that group, because they were doing what I thought was really important. And internally, they didn't seem to realize that this was like a huge deal for the world. Their main thinking is, we want to make mathematicians' lives better. We want to prove the mathematical Olympiad. We want to be able to solve those problems. There didn't seem to be any inkling that this is like the core of safety and of software generation, all this kind of stuff. So I'm a little frustrated that proof, it's somewhat esoteric. It's not that easy to really understand the nuances, but it's really the core, I think, of doing precise and provably correct systems.
Yeah, so AI, from what I'm hearing now, is clearly getting better at mathematical proof. I think the skepticism about the approach is more, you have some complex behavior that you want to forbid. You want to forbid the system from being deceptive or from breaking into some other online system. How on earth could you formalize a notion like deception and then prove that a system cannot do that? You went through the history of formalizing the world, but I think you would also acknowledge that it's been a kind of recurring problem that the world is often complex in a way that escapes our formal systems.
Absolutely. And so in this paper with Max, at this point, I think eventually we will get there, but this is urgent, so we don't have time for eventually. And so fortunately, we don't need to control the absolute fine details of all this. An analogy I kind of like to think about is, we have cars driving on roads, and, that's not that old of a technology. And they had to figure out all the stuff we take for granted now, stop signs and traffic lights and lanes, all that. None of that existed early on. So they had to figure out rules to keep these powerful new technologies from killing people. And there are subtleties to it, right? So today we have rules about how fast you're allowed to go on a road, and what are the rules for like passing somebody, and we have these blinking lights to stop when you stop, all that. But the really critical thing is, if let's say you're driving on a road around a cliff, you don't want that car going over that cliff. So that's an example of an existential risk, right? Somebody does that, and they're probably not going to survive. Yeah, it's nice to have the nuances of how you pass the car and what your speed should be, all that kind of thing. But really, we want to be darn sure you don't go over that cliff. And so we invented this little technology, the guardrail, which is this little teeny fence that most roads on mountains have, that if a car hits it, it tends to bounce off, May not be good for the car, it may get dented, whatever, but you don't go over the cliff. And so we have this hard barrier, restricting a certain outcome, preventing a certain outcome. It's cheap, easy, and it's coarse, right? It doesn't really know the nuances of, maybe the guardrail is there when somebody doesn't want it to be, in some way. But hey, as a starting point, it cuts off the really risky outcome. So I think we need the analogous thing here.
What is analogous to a guardrail in the AI case?
It doesn't really have much to do with the AI itself. I think it's great to try and do alignment and make the AIs good, But I think it's more about the world, systems in the world which are potentially really risky. And we know pretty much what they are. Launching nukes, really bad. You don't want your AGI to be able to launch nukes. Releasing, smallpox, bad. Don't want that. Maybe we even want to think of large data centers full of GPUs. Maybe that's a risky device. So that's a mechanism for controlling AGI. Maybe only certain, very carefully vetted groups get to train their models on big data centers. It's a sort of a restriction that prevents some bad outcome on the other side.
Yeah, you want to start with the most critical systems in the world.
Exactly.
Okay, let's begin digging into the details of the approach. I think starting with provable contracts. What are these provable contracts?
So what do we need in order to limit a device? Think maybe of a robot, a drone, or maybe even like a DNA synthesizer. And we've got some AGI maybe out on the internet somewhere who says, yeah, I really want to make some DNA. And I got some money, I don't know, it's a few dollars a base pair or something like that. It's pretty cheap. Should this, DNA synthesizer do what this AGI is telling it to do? Well, we need to have some rules about that. And we need those rules to be automatically checked. We don't want a human in the loop. We do probably want humans to help in the making of those rules or the shaping of those rules, but that's a whole different story. Let's assume in some way we know what the rules should be. How do we ensure that those rules are followed?
Why is it that you want a human in the loop for specifying the rules, but not for applying the rules, so to speak?
Because what exactly the rules are, if we're very clear, like let's say the one and only thing we want to do is prevent human extinction, I think that's fairly clear. So killing all people is the bad outcome. And so we go backwards from that. We put little guardrails around the trouble is, especially if you're doing really coarse guardrails, a good way to keep technology from killing everybody is to lock everybody in little cities with no electricity. We eliminate all electricity in the world. But yeah, that'll keep us from. So there are bad ways of meeting that goal. And so you do want to have what humans value and care about, the sort of an alignment question in choosing what your course protective goals are. As we implement this, assuming this is the direction we go, we'll discover we put too many limits on this DNA machine. Now it won't make a drug we need. Okay, so we didn't get the rules quite right. How do we fix that? Or oh my God, the AGI figured out a way through this class of rules. That was bad. So we need a whole mechanism for first creating the rules and for updating them. But that's really risky because if you have a way of updating rules, well, that's what AGI is. That's a vulnerability, right? That's an attack vulnerability. So how do we prevent that? We could have one person. I'm the keeper of the rules for the DNA machine. Well, then that person is now a target for AGI. So generally, the way we do that today is we have groups that do it, and we have voting mechanisms. And so I think particularly for rules at the societal level, voting is a great system. There are nuances. I think today's voting mechanisms are really, really crude. Robin Hanson has something called futarchy, which is a subtler, better thing, where maybe we can even use AGI in choosing how to do the voting and where to get info and how to build models that then people can reflect on and make decisions. So we need mechanisms for choosing what our rules are in a smart way and also showing that the rules don't have vulnerabilities, right? So we want to be doing simulations of them. That's a whole story that I think Max and I just kind of hint at a little bit. I've thought some of it, but I think there's whole disciplines needed there. And maybe there are people that are doing kind of formal models of society and what are the social mechanisms. The framers of the Constitution, they laid down these rules, but they also wanted to leave room for amendments, so ways to update them. And so pretty brilliant, but we need to invent systems for that.
Yeah, so we want humans in the loop for creating the rules. But then when some string is sent to a DNA synthesizer, we don't want humans in the loop there because humans are too slow and humans might be manipulated. So we want some unbreakable system to not create that DNA.
Exactly. So what does it mean? So first of all, it has to be a program which checks it. But programs have bugs and all kinds of problems. Well, this is where the amazing power of mathematical proof comes in, that if we can express the rules that we want to be satisfied precisely and Zermelo-Fraenkel set theory, that's my favorite, though these days it looks like lean, which is based on a type theory, is much more popular at the moment. So maybe it's a type theory, based system. The reason I don't like those as much is that they're pretty complicated. The great thing about Zermelo-Fraenkel set theory is it fits on one page, and so, and the checker is, 300 lines. So that's a, teeny, completely understandable system. But whatever it is, and, all the theorem proving systems are essentially interconvertible. You can prove anything in one and transfer it to the other. Not easily today, unfortunately, but theoretically, it's that way. So whatever it is, you force the AI that's proposing a certain thing to provide a proof that it meets your needs. Some of those needs might be, I want the okay of the director of the CDC. And here's his signature saying, yeah, this is a great anti-flu project, and we verified it. We think it's great. So, in today's world, you have groups of people that are, committees that sort of look at, is this a reasonable project? And we can just drop that down as long as we make a machine checkable version of that. But eventually, we'd really love the details of the biochemistry, that what's allowed and what's not, what's toxic, what's not. We'd like that to be as a part of this criterion. Just need a little program running on a little teeny processor, and it checks the thing. And if it's verified, it then sends it onto the machine. Everything's hunky-dory. Sounds trivial, sounds simple, except an AGI is very good at breaking into systems, understanding systems, manipulating systems. And so if our little checker is running on, say, a typical microprocessor, well, there are all kinds of ways to manipulate microprocessors. So we need something special there. We need something which cannot be manipulated by an AGI. And when it says yes or no to the DNA synthesizer, that command should not be manipulable by the AGI. And the synthesizer should not be manipulable by the AGI. And so that's where we get into sort of a little bit of the hardware that underneath it. And if you have enough energy, so people break in, there are these secure enclaves today. Apple actually has a really nice one built into almost all their products now, I believe, including the Apple Watch. So the Apple Watch has its own little secure enclave in there, which has its own analog random number generator, so it can generate random keys that have no influence from anything outside and can't be seen from the outside. Has can do various kinds of cryptography on there. And they have some tamper resistance that they don't talk about. So I don't know how strong it is, but it's sort of a hint of the Apple Watch has a protected environment where you could run those proofs in that secure enclave, and it would not be breakable by the standard easy mechanisms. But if your AGI has access to robots with, scanning electron microscopes and lasers and this and that, they can it'll pretty much be able to break into any physical device. So what do we do about that? How do we keep the whole physical infrastructure from falling apart? Well, there's a very simple, clean idea that I just love. It's old. It's from like the 1960s, called zeroization, which is you have some cryptographic system that internally has some secrets in it. And you have sensors which detect any attempt at tampering. And if they detect tampering, they delete the keys, or even delete all of the secret information. Apparently, Soviet jets had this. There's a great photo on Wikipedia of a little switch that's, if the jet is going down, flick this switch and it deletes all the secrets that are stored in that jet. And so what this does is you have this little hardware thing that you can, assuming you make the sensors so that they really detect all the ways that any agent might physically probe it, breaking into it, lowering temperatures, zapping it with electricity, whatever, anything that's out of the normal range of behavior, or any kind of attempt to drill into the thing or whatever, it deletes all the keys. Then those bits, it's quite a unique thing. We have a little teeny physical device with some secret bits in it that literally nobody can get access to. And eventually I would love to have a physics proof of that. Prove that no physically possible attempt at attacking this thing can get at those bits. The downside is that becomes a denial of service attack also. Let's say we're in a war and you've got AI robots coming at you using this technique. Well, as long as I try and attack their secret keys, then the robot stops working. And so it's a little bit, you have to worry about that. And you also have to worry about losing information at the systems level. So this is a component in a much bigger story. So that, I think, will enable us to have an enclosure and a physical device that we're guaranteed won't be broken and that can do computation, and we can have proofs that computation is done correctly and is not manipulated.
So what we're imagining now is a world in which we have all of these critical systems. We have nuclear facilities, we have biolabs, AGI corporations, and in the way they operate, they have secure hardware running provably secure code. And the hardware is tamper-proof to the greatest extent possible. And this we have specified by some social mechanism what it is, which kinds of code can be run by these facilities and by these labs and so on. Is this the end goal of this network of provable contracts for you?
Well, maybe it's the end goal of the first stage. So if you view our first goal is prevent human extinction, simple, clear mandate. And I guess part of it's a little less clear in that we don't exactly know what all the pathways toward that are, but we know some of them. And so I think that technology alone would do that. I think we can, protect the biohazard labs, protect the nukes, protect the, AGI data centers, whatever. And then, but this technology, once we've got it, let's say we really have it done and we make it cheap. So we have these little, provable contracts or, $1 a module or something like that. We can start using them everywhere and get all kinds of other social benefit out of it. That step, I think, is much subtler and will require modeling human thinking and human values in a much finer and more detailed way. Once we prevented extinction, then I think we have plenty of time to, really think about what we want and make that happen.
I think one worry here is that imagine that this network of provable contracts becomes more and more complex, and it becomes layered and begins to rely on parts of itself in kind of interdependent ways. What if there's a bug in one of these contracts, which is a computer program? So it could be buggy, right? What if that bug then kind of spreads out in the system because other provable contracts are dependent on the buggy provable contract?
Well, so part of the design of these things is that they are fully verified, so they're not going to have bugs like today's programs have bugs, some pathway, but they might have bugs in the sense of they're saying that they're imposing a rule that turns out not to be the rule we really wanted, and so that's a huge risk. And we're going to need design principles. How do we design, particularly networks, complex systems of rules that interact? What I think this technology would do is it gives us a sort of base that we can absolutely trust. And then on that base, we can build up whatever we want. And so on the good side, we can build the most utopian, fantastic society. I think there are ways even to prevent, prisoners' dilemmas and social dilemmas and tragedies of the commons, all the problems that today's society struggles with. I think we can solve all that with this. On the other hand, particularly if some draconian force got control of the designing of these things, we could create, a terrible dystopia. And so it's a sort of morally completely neutral technology that enables any social system that you want can be implemented with this. And so the challenge is, how do we ensure that we get, and I think we can use AI for that. I'm really liking this idea of digital twins. NVIDIA has really been pushing that. Lots of companies are making digital versions of their factories where they have every piece of equipment in that factory has a digital version, and they track and they have sensors all over the factory, and they keep the two in line with each other. And based on the sensor data, they learn what the behavior of the systems is. So they can, for example, predict when you need to do maintenance. Apparently, just predictive maintenance is like a multi-$100 billion industry, and so it's very, very valuable in the factory setting. I think eventually we're going to have that for the whole of humanity, where we need digital twins of ecosystems, of forests, of, is this forest, vulnerable to forest fire? And what are the smallest changes we can make to fix it? So I think we will just very naturally have digital models for all of the systems in the world, and then proposed, rules that we do. We can simulate those, and we can do mathematical proofs within those.
So we can kind of test what the effects of the proposed rules might be in these digital twins. One worry there would be, so at what level of detail will we have to simulate these digital twins of our factories and so on? And I think specifically, will the digital twins of parts of the world have to include humans? Because then it becomes very, very complex, right? If you have to simulate the behavior of humans. But I can definitely see the application for finding out whether your factory is safe, or perhaps whether your critical infrastructure is safe.
Absolutely. Yeah. Today, they're really doing that. And the human piece is really interesting. I actually wrote some papers and did some talks on something I call personal AI, which is the idea that each human will have an AI that is theirs, that represents their interests in the world, and how you actually do that and make sure that it's not, manipulating you or whatever. That's a whole story. But let's assume we had that. It solves many, many of the issues. Like with today, with social media and so on, all these social media sites are trying to send you ads that will manipulate you and show you, posts on tweets on Twitter that are will annoy you, so you'll respond and engage and so on. If you had your own little personal AI that knew what you cared about, what your true deepest values in your contemplative point would be, and what your capabilities and so on were, it could shield you from all that. You could say, I'm vulnerable to alcohol. Don't show me any alcohol ads. Or I tend to get sucked into gambling. Never show me gambling. And now your personal AI shields you from all of that. And now the companies which want to send you that stuff, it's not working. So now they have no incentive to create that kind of ad. So I think a society in which each person has a sort of AI agent that represents what their interests are. And now in votes, your AI agent can tell the society, like, oh, he really wants more schools and he doesn't really care so much about, the potholes on the road or something. And so in votes, you can have, detailed information from each citizen's personal AI.
Kind of a digital optimal version of yourself acting on your behalf and protecting you. And interesting. Let's talk about proof carrying code, because this is really a central part of this approach you take to AI safety in the paper. What is proof carrying code? How does it work?
So that was an idea, brilliant, amazing idea. George Nekula, and I think it was 1999 at Berkeley. I think he did his thesis on it, wrote some papers. People are starting to have code which moves, like JavaScript, runs on your computer. Somebody else wrote this code that runs on your computer. How do you trust it? The whole area of formal methods really just got started in the 1980s or so, is using mathematical proof to ensure that your code doesn't have bugs in it, and also hardware. Those are both there. And his idea was, your compiler, which is compiling this code, should be able to check that certain, that it's, say, memory safe. It doesn't have memory leaks, or it just uses up more and more and more memory. You can prove that kind of thing pretty easily. And that proof should be a part of the code itself, so that when you give it to some other machine to run, it can check that proof before it runs it and be sure that the code is not going to fail. The types of things that they could prove back then were pretty limited. Things like that types are safe and so on. But the idea, I think, is super important and brilliant. So we sort of want to bring that up into the modern age, where now we're going to have AIs. We now have AIs that can generate code left and right. We have all these large language models for code. Of course, they often generate code with bugs in it, which is a problem. So we'd really like code which is provably meet some spec and provably doesn't leak secret data or have infinite loops or memory leaks or all that kind of stuff. Surprisingly, that sort of doesn't seem to exist quite yet, but I'm guessing maybe even Google's been sending little hints about what Gemini, their hot new model coming in December, supposedly the rumor is, and they say it's going to be a large language model combined with techniques from AlphaGo. And so maybe that'll have theorem proving in it. I don't know. I think that the first group or company that combines language model type technology with theorem proving is going to just explode, because once you have theorem proving, you can generate your own training examples. You can try a bunch of different stuff out, and if you find one that provably works, now you have a guarantee of that. And so you don't need human training anymore. And we saw with AlphaGo, oh my God, AlphaGo, the first version trained on human data, and then the next version, I think it was Alpha Zero or AlphaGo Zero, trained on only playing itself, and it was even far better. And then they did Alpha Zero, where it also did chess, and apparently, I understand that in 4 hours it got to a level where it could beat all humans. So all of human chess knowledge was created by the system in 4 hours. So imagine you do that with mathematics and the mathematical structure. Oh my God, no telling where that's going to end up. And in particular with code and provably correct code. So Now, instead of generating little snips of Python, which, based on what it learned off of, GitHub or something, it will generate provably correct code, provably optimized in this way and that, with provable, properties of no leaking and no this and no that. Oh my God, it'll be a new era.
So you don't think lack of training data will be a problem in the long run if you combine large language models with theorem proving?
From the current language models, we probably have most of what we need from human civilization. Google's also rumored to be training on YouTube videos. So video also has more stuff. So, but that combo is probably, probably anything anybody has thought about that is really deep and significant is somewhere in some book or on some video somewhere. And so the human contribution will come from that. And then once you've got that, you can now go wild in designing. The system can check itself.
So what's the advantage there when the system outputs something that's provably a correct solution? How do you generate new synthetic data from that?
Well, you can do various things. You can, for example, find let's say you've just found a really cool new algorithm. You can find a formal summary of what it does, and then you train it on find an algorithm to do this. And we know what the answer is, and we provably have it, but we force it to learn that. And so in general, it's a good technique to, like many of the current models work by taking known examples and then either adding noise to them or deleting parts of them, and then asking the system to recreate the part that was noisy or missing. And that enables them to learn the detailed structure of everything, and they just get better and better and better at that.
Returning to the approach to AI safety in provably safe systems, there's this big issue for me around creating the specification that the code must satisfy. Is this more of a philosophical problem? Is this more like solve ethics or, solve human interaction, which seems to be, very far from a solution? Even though the underlying mathematics might be enormously advanced, potentially we don't know what it is that we want to do with the specification of what the code can and cannot do.
Oh, yeah. I think that's a critical and fundamental issue. In the history of AI, there have been two camps that are these days not so visible. But like when I first started learning about AI in the 1970s, they used to call them the neats and the scruffies, where the neats were all about mathematical logic and precise models and proof and everything. And that was sort of John McCarthy, who started the AI lab at Stanford. I studied with it when I was an undergrad. I took some of his classes, and he had us proving things about Lisp programs. And so that I kind of think I got shaped quite a bit by that. On the flip side was Marvin Minsky, who was at MIT, and he was like one of the proponents of the scruffy approach, which is, no, brains don't have logic in them. They are little cells that you throw a bunch of cells together, and they randomly grow, and they train and learn. It was all about machine learning, neural nets, and all that. And early on, they were totally disparate. And the pendulum has sort of swung back and forth. When I first became an AI scientist, neural nets were on their ascendance. Hinton and Rumelhart had just written these books about neural nets, and this was the mid 80s, and everything was going to be great. But then Japan came out, and Prolog was the sort of leading neat approach, neat logic-based things. Japan had this 5th generation project. We're making Prolog machines that are going to change the world and everything. And there was this big race between Japan and the US. These days, I don't think those battles and crazy things are even in people's consciousness. So it's sort of funny how, and so a large language model is a formal model, right? It has, precise mathematical, multiply this 4-bit number by that 4-bit number and do this, and you get some answer. The trouble is it's not self-consistent. I mean, the two big issues with today's language models is if they don't know something, they'll just make it up. So they hallucinate. And their logical reasoning steps, they're learned. And so if some human has had a similar kind of step, they might have learned about that and they do that, but they're not precise in any way. They don't have precise reasoning axioms, but they're pretty close, right? They're trying to capture human reasoning. And so there's a wonderful paper that just came out, maybe a month ago, called From Word Models to World Models by a group at MIT around Josh Tenenbaum, who just does amazing work. He sort of tries to combine human psychology with AI. And they argue that language, natural language, is only a teeny piece of thought. and that we really have a language of thought, and that all animals have a language of thought. Your dog is figuring stuff out. It's doing reasoning, even though it can't talk about it in language. And they propose that a formal model for that is something called a probabilistic program. They use the program Church, which is sort of a probabilistic version of Scheme. And they use large language models to translate from natural language, which is sort of fuzzy and not so clear, into this precise model. And they show how to do it in a number of different domains. And then you do pure Bayesian reasoning, precise, absolutely correct, and then translate the results back. And so anything that you can do that for, you can easily get the language models to create formal models. And so they do it, I think, in that thing for physical reasoning, for social reasoning, for relational reasoning. And they tie it with what's known about human thought. Daniel Kahneman has a story that there's system 1 and system 2. System 1 is sort of the really rapid, quick, kind of fuzzy, and that's what our language models are like. System 2 is the more systematic, step-by-step thinking. And I think that's probably where things are going, maybe later this year. I don't know when. And so that part is precise and formalizable. The fuzzy part, not so much. Physical concepts, we have the laws of physics, which are totally precise and at least in this, around the solar system, believed to be, we can represent pretty much any phenomena. And so anything physical, we can build up from physics and have a formal model for what's going on. Subtler concepts like, states of consciousness, that kind of thing, maybe not so clear.
I mean, it's also the case, I think, that the fuzzy language models are beginning to approximate human logical reasoning. I've been pretty impressed by what's come out of OpenAI's models, for example. You can give them some logical puzzles that previous versions of these models couldn't solve. Like, you have Alice and Bob in a room, and there are 4 apples on the table, and Alice all of these. The specific example doesn't matter, but they can solve logical reasoning at a higher and higher level. And so maybe the kind of fuzzy approach begins to approximate the formal approach.
Yes, I totally think that's true. Also, transformers are pretty limited in, they only have a finite number of steps. I forget what the current ones are, 32 or something like that. But if you'd say, let's take this step by step, or let's do chain of thought, now you sort of spread it out and you give it more room, to make longer arguments. And so I think you're totally right that I think these models they're picking up on, much of human language on the internet is people making arguments about things. And so you get enough of that, you get pretty good representations of the steps. So it's not that hard to convert that to an absolutely precise model. In fact, one of the big efforts, which I think is super important, but again, kind of under the radar, is auto-formalization. A group that was at Google, Zaghetti, I think, was ahead of it. I think he's just moved to Elon Musk's new AI company, X.AI, something. So I don't know what those guys are up to. But auto-formalization is you take human-written, say, math books or physics books or manuals for programming languages or manuals for hardware, and you read it in a large language model, and then you convert it into a precise formal model. And then you can prove theorems about that formal model. And I think that's super important. And that once you do that well, and they've got some early trials which seem to be working pretty well, you should be able to suck in all the world's math books and get not only the underlying, theorems, the statements of the theorems, the definitions of all the mathematical objects, but also the proofs. And typically in books, humans don't lay out all the details of the proof. They say, well, it's as left to an exercise for the reader, you do this, this, and this or something. But I think current AI theorem provers can do all that type of stuff. Maybe they can't get the brilliant insight behind the theorem, but they can certainly fill in all the details. So I think we can pretty quickly automate all of the world's mathematics and all of the subjects which are built on mathematics, like physics and engineering and economics and so on.
And this would help us create the specification for what it is that these AI models can't and cannot do. So if we have formalized versions of all of our knowledge and perhaps some of our logical reasoning and some of our common sense, that this might help us in the way that we can better specify what it is that we want to, the kind of nuanced things that we want to allow and not allow AIs to do.
Exactly.
What do you think are the most difficult areas to formalize here?
Well, I mean, philosophers have been struggling with like various ethical philosophy for thousands of years. And I'm not sure, like the trolley problem is one that in some variant shows up in a lot of AI systems. Self-driving cars, they can either crash into a car in front of them or run over the motorcyclist to the right of them. Which should they do? So there are these ethical issues that just pop up everywhere. I haven't seen any, universal agreement. Yes, this is the right version. Or political philosophy. We have China and we have the US with very different priorities about how your society should run. So I don't quite know, AI is going to make it possible to make those systems really, really be implemented. I don't know how you choose. And I guess voting is sort of allowing humans as a group to contribute their beliefs and values, I think is a way to, at least avoid some crazy person, taking over the world kind of thing.
Yeah, and I think we can always fall back on thinking about you could call it low-hanging fruit of securing critical systems so that humanity does not destroy itself. Let's talk about automated software verification. How is it that we can use AI to prove that some piece of code meets these specifications?
Well, let me give a little bit of the history, because this is unfortunately an area that I've been somewhat frustrated by. I mentioned that the foundations of mathematics, or Mello-Frankel set theory, were really laid down in 1925. As computers started coming around, they started realizing, oh my God, we can make digital equipment that implements some of this stuff. Alan Turing invented the first formal digital model of a computer and proved all kinds of theorems about it. That was the Turing machine. It was a foundation for computation theory. He also, in some writing that isn't as well known, did the very first formal verification. He showed how you could use mathematical proof to prove properties of programs. And that could have lit a fire and had everybody do that. And all of software engineering could be based on formally proven correct programs, and we would have much better technology today. Unfortunately, that's not what happened. The world invented Fortran, and they invented, Algol and all these little, languages, and humans got pretty good at writing programs, but they had lots of bugs. And then they started doing parallel programs and programs that communicate with one another, really complicated interactions of, what order things happen in. And humans are not very good at reasoning about that. So there are all these bugs. And so we just had, a litany of terrible stuff. And around 1980, the field of formal methods sort of got named and got really started to going. Intel in the mid 80s sometime had this terrible problem called the division bug in their processors. It turned out that the arithmetic unit which did division had some bug in the logic of it that nobody had caught. And somebody found it, and spreadsheets would show the wrong answer if you did the wrong kind of division. This is a terrible embarrassment for Intel, and I think they ended up having to replace a lot of chips. It was hugely expensive. So at that point, late 80s, Intel hired all the formal methods people they could find. And so Intel became like the center for that. And I assume that they used it to make their chips better and avoided, that kind of bug. Instead of going down the route of let's take software and hardware and represent it in these very powerful general mathematical languages like Sir Mello-Frankel set theory, they invented their own special languages. So they're like special little rules, like if you have this precondition, we guarantee that postcondition. We have loop invariants. And they invented tooling, which was very specific to a certain way of doing proofs, which worked for a limited thing, but did not generalize to the full statement. You can't go to a typical formal method system and say, we need to sort here. Is this sorting algorithm correct? I think that has meant that, in a whole field, they have conferences every year, do all kinds of stuff, but it hasn't really progressed to the point where most people are using it. Some cryptography software, where bugs are really, really critical, they use it. Blockchain, smart contracts on the blockchain, there's millions of dollars at stake. And many, many smart contracts have been broken because somebody didn't think through the code very well. I have a friend who has a blockchain company doing a stable coin. And he was just telling me that, we hired a group to do formal evaluation of our code. I said, oh, that's great. You formalized the whole thing. He says, well, no, they couldn't do the whole thing. Our whole thing is like 1,000 lines of code. And that would have been way too expensive and taken years. We just had them do like the inner loop, which was, 20 lines of code, but they really got that down, And so it's like, what is going on? So from my point of view, all of this stuff, all programming languages, all specification languages should all be mapped into some universals or Mellon-Frankel set theory or type theory or whatever, and full power of mathematics should be imposed on it. Hasn't happened.
And for that, we would really need AI to help us, right? We couldn't formalize all of this ourselves.
Well, we could, but it would be painful. And so like the history of mathematical theorem proving, there was a group in 1990 called QED of these very forward-thinking mathematicians. We really need to make mathematics be digital, be it on the computer. It's going to be great. And they were like gung-ho, it's going to be great. Then messaging, lists and so on, just petered out, didn't happen. Problem was mathematicians were not particularly interested in computers. They didn't really want their proofs to be checked automatically. It didn't see any value in that. The people who could use mathematics didn't have a clue what all this crazy math stuff was. So somehow like a cultural gap. And I think you're absolutely right that proving is hard and it's much harder. It's harder than programming. And programming is a pretty challenging task. Formal proofs tend to be about 4 times as long as informal proofs. So they're somewhat bigger, but they're not terribly bigger. It's called the De Bruijn factor. I think that AI theorem proving hopefully will revolutionize all of this. So, right now we have a Copilot from Microsoft is, generating some stuff, but who knows if what it's generating is right or not. Imagine Copilot with formal proofs of generating it. And then all the modules are proven and they all come together. I think there's only about maybe 50 or 100 really core algorithms in computer science. How do you do sorting? How do you do searching? All that kind of stuff. Those are a little bit challenging to prove. You have some, mathematical problems. Almost all of programming is sort of gluing those algorithms together, making sure the data is in the right form and you go through this and that. And so proofs are really just gluing together proofs of little pieces. So I don't think from a mathematics point of view, I don't think it's particularly hard. It just culturally hasn't fit into the way our systems work today.
And you think that there's a bright future for AIs proving things about our code?
Absolutely, yeah.
What would be helpful there? In the paper, you mentioned having better benchmarks and something about developing probabilistic program verification.
Well, so several different things there, and partly it's Max and partly it's me. So in the very short term, the way that we could build these systems is, say, by training a large language model to do it. And for that, you need a training set. And so several of our, suggestions for the future are build a training set. So one is a training set for verification. If you want a large language model to take in some code and some property and to prove that property, well, we got to give it some examples. So that would be really, really valuable and immediate. Another is mechanistic interpretability. So given a large language model, how the heck is it computing what it's computing? Right now, humans go in and measure and try and see, this neuron goes on when this happens. Well, we should automate that. And so how do we automate that? Well, we need another data set for that. The next is, it's easiest to think about deterministic programs when we want to prove properties about them. But that work that, say, Josh Tenenbaum and so on is doing is really basing everything on probabilistic programs. And there are some very cool probabilistic programming languages. I used Pyro, which came out of Uber, actually, but now is, I think, an independent thing. Beautiful, lovely language that allows you to express any probabilistic relationships, arbitrarily complicated probabilistic grammars, all kinds of stuff, and do Bayesian inference on it and so on. But it's not provably correct, and it doesn't generate a proof that once you get an answer out, that answer is actually right. And so, and there are approximations in doing the Bayesian stuff the way they do it. And so, it's a little bit of we tried it, we got this, kind of thing. And so I think we need to move all of that tooling over to the formal side so that we can really be sure of the answers. In fact, I hate to say this, again, kind of being a gadfly, the whole field of doing scientific computing, numerical analysis and so on, all of that should be formal. And all of those things should have provable bounds on what the outputs are so that you can trust them. You run some code through a fluid simulator, you have no idea. A numerical analyst analyzed it and he said, well, I didn't see any places it would fall apart. That's just not sufficient for the world we're entering into. And so a lot of scientific work needs to be done there. I think a lot of it can be automated.
One advantage of the approach you're sketching here is that it's easier to verify that a proof is correct than it is to discover the proof itself. So you might have AIs discovering a proof and then humans verifying that the proof is correct.
Exactly.
Say that in the future we have a very capable AI system, and it comes to us and it says, oh, what you need to do is to implement this plan. And the plan is 120 steps, 10,000 lines. We have no idea what that involves if we run it. If we have proofs that this plan does not involve something that we've pre-specified that we don't want, right? That's great. And we can then verify that the proof is correct. Maybe tell us a bit about this difference between discovering a proof and verifying that proof.
Yeah, in some sense, the theoretical computer scientists have the most important question underlying all computer sciences is P equal to NP. And P is the class of things where it's really easy to solve the problem. NP is a class of problems that you can state, and if somebody hands you the answer, you can check the answer very quickly. And so that's a fundamental question, and we're still unresolved. Probably AI is going to help a lot with that. It may be that it's undecidable, so we don't know, but it's really core to a lot of these issues. And unfortunately, almost all of the tasks in AI are actually NP complete. In the 1970s, they found a certain set of problems that if you could solve them, you could solve all the NP problems. So if you could solve this certain problem, and it's sort of like the core one is something called satisfiability. And that's basically you take a circuit made out of ands and ors and not gates. And the question is there an input to that circuit which makes the output 1? Say there's one output and multiple inputs. And it turns out that is a universal problem that you can convert any other NP problem into that. It was thought that probably the sort of general consensus is that P is not equal to NP and that there actually are hard problems where finding the solution is much, much harder than checking that solution. And so in the 80s, everybody was saying, oh my God, trying to find the 3D structure of this image, that's NP complete. That's bad. Robot motion control, that's NP complete. That's bad. We just sort of throw up our hands that if it's NP complete, it's hopeless. Well, in the early 90s, Bart Selman and some other people started actually doing tests. And what they discovered was for example, most satisfiability problems are actually really easy. And there's something called 3-SAT, where you have a formula which is just a conjunction of a bunch of disjunctions with 3 literals each, and each literal is either a variable or its complement. And people started studying random 3-SAT. And it turns out if you have only a few clauses, few constraints, you can think of it as a constraint system, you have only a few constraints, well, then it's very easy to satisfy it. And in fact, almost any search method will find a solution really, really rapidly. So with a few constraints, it's easy to solve. If you have a huge number of constraints, they're almost surely incompatible with one another, and there's no solution, and it's easy to check that. So at the two ends, it's really trivial to find solutions. As you start throwing in more and more constraints, it gets harder and harder and harder, and then at some critical percentage, it becomes really difficult, and that's where the potentially exponential searches come in. But almost all the problems are actually easy, and these days, SAT solvers can routinely solve million variable problems in the real world.
If I understood that correctly, many of the things we want to do in computer science are such that we can more easily verify that a proof is correct than we can discover that proof. Is there anything that's beyond that?
Oh, yeah. Well, the theoretical computer scientists have created huge hierarchies of ever more complex things. So there are all kinds of problems which you can't even verify if you've got the right answer.
But in terms of the real world behavior we want out of our computer systems, is there anything where this nice kind of feature of the proof being more easy to verify than it is to discover breaks down?
Well, I mean, there is the piece that many finding the proof, as you get smarter, finding the proof gets easier and easier. And so brute force attempts at finding proofs can be really exponentially bad. But as you get to be a better mathematician, you know these special tricks, and sometimes the tricks involve really weird stuff, like Fermat's last theorem is a classic example where it's very easy to state, just multiplication of some numbers, taking things to powers. And yet to actually prove that it was true required developing a huge amount of mathematics seemingly totally divorced from that. And so I think that's a pretty general phenomenon that sometimes in designing something or creating a proof, you need to invent ideas that are way beyond the original context. But once you've done it, then it's pretty easy to verify. So
yeah, this probably also means that Fermat did not solve the problem in the margin of his book.
Or at least his proof had bugs in it. He didn't have a theorem checker.
All right, let's talk a bit about mechanistic interpretability. What is this, and where does it fit into the approach?
So, the alignment people are all about, can we make our AIs, have properties we want? The sort of extreme of the provable systems thing is forget about the AIs. They can do whatever they want. We want to limit what they can do in the world. Mechanistic interpretability is sort of in the middle. It's like, let's see if we can actually figure out some of what is going on in the AI. We may not be able to understand it fully enough that we can actually put provable constraints, say, on a large language model. But if we know how it's doing what it's doing, that will help a lot in spitting out a formal model that we can put constraints on that captures whatever, the domain is for the language model. Particularly if we're focused, like these large language models, they know everything about everything, right? They've read the whole internet. And yet maybe we're only using them to, control a DNA synthesizer. So we only really are focused on a teeny subset of its knowledge. And it may be that we can create a formal representation of that piece of knowledge very clearly. And we can write a teeny little program that does whatever it is we want it to do in that domain. And then that formal verification we can use directly in the provable proofs. And so that's an example of why it would be valuable to have understanding of what's going on inside these models, even if we don't really intend to try and formalize the whole thing.
We could understand it as a form of digital neuroscience in which you try to get at the algorithm that the program is running in order to create the output that it's creating. AI systems, machine learning systems are black boxes, but we can understand parts of them by doing this mechanistic interpretability work. I guess one worry I have here is whether mechanistic interpretability can move quickly enough in order to matter at the timescales we're talking about here. It seems that if we're doing it by hand, it's not going to work, but maybe we can do automated mechanistic interpretability.
Well, first let me say, I don't think the mechanistic interpretability is essential. I think we can do the guardrails even if we aren't able to do that yet. So it's something that I think may unfold over time. One thing that's a little funny, and Max and I had an interesting discussion about this, you can ask large language models why they came up with the answer that they did, and they'll make up a story. And the question is the story they're telling you about Sally has 4 red apples and, Bill has 7 red apples and Sally ate one of her, whatever. And how many are there? Oh, there are 17. Well, why did you say 17? Well, because of this, this, and this, and this. And so you say, oh, great. Here, this thing has knowledge of its own thought, has a knowledge of its own thinking process. But really what it's doing, it's not looking internally for that. It's saying, gee, if a human were asked that question, what would they say?
The funny thing is that it may be doing the same thing that humans do in that situations.
Yeah, it may be that, there is this whole thing that humans do, they sometimes call confabulation, where there are these split brain patients and they can show like one half of the brain one thing, and then they ask the other half why they did something, and it makes up some story. Totally, the human makes up some story, that's totally wrong, and we know it's wrong. So I think the language models are you're absolutely right, are pretty much doing that right now. So that's kind of interesting. But we can take a second language model looking at the activities of the first language model, and it can then probe that and do experiments and so on, and then make, actually figure out what's going on in that first one. And so, yeah, that's an example of automating it. We mentioned formalizing probabilistic programs. I think that's important. Max also wanted to say, well, we also want to formalize quantum programs. So just thought I'd throw that in there too.
Would that be necessary for securing the critical infrastructure, or is that a problem that's further out?
Quantum computing appears to be very valuable for things like designing quantum molecular systems and for breaking a lot of today's cryptography. So today's public key cryptography is all based on systems which have fast quantum algorithms. And so the quantum NIST actually calls it the quantum apocalypse. And nobody quite knows when it's coming, but we're probably going to have to change much of the algorithms that the internet is based on, and many of the algorithms that like blockchain is based on. And so that could be a secure. So I'm trying to do the designs for provable contracts, not relying on any public key cryptography, because that just seems too vulnerable. I'm even worried about private key cryptography, which is believed to be on a firmer grounds. But because we can't prove P is not equal to NP, we can't prove the critical things, sort of existence of one-way functions. Fortunately, there's a whole subfield of cryptography called information theoretic cryptography, which has no assumptions. It actually is provably unbreakable, but it's a little more awkward to use. Something like the one-time pad is sort of an example of that, but you have to preposition keys. And another one is Shamir's secret sharing. And so you can use that together with hardware cryptographic primitives to not have to rest on any assumptions like the public key assumption.
You mentioned a potential problem here that might be an enormous problem with this approach, which is that if the specification of what the programs can and cannot do falls into the hands of the wrong group of people, that this might become dystopian. What I'm thinking about here is imagine a world in which you're not allowed to do anything, and this is controlled at the hardware level by some totalitarian state. How do we avoid this? How do we avoid creating the grounds for a dystopic future with this approach?
Yeah, I think that is really important and really critical. I mean, I have just pretty much initial thoughts. So the first initial thought is, you shouldn't just Joe Random shouldn't be able to create a contract, a provable contract that governs something really, really important. We should have rules about what that contract should and shouldn't do. Well, where are those rules? Well, those should be in another contract, and I call those meta contracts. So we should have meta contracts which control the modification and creation of other contracts. And those go, unfortunately, mathematical proof is plenty rich enough to be able to prove properties like this set of constraints is consistent with this set of constraints. And so you can imagine a hierarchy of those. And up at the very top, you have something analogous to, say, the US Constitution, which and maybe the Bill of Rights, which says, every human has this right, this right, this right, and this right, and no law shall violate those rights. Well, you can actually if you could say that formally, what you mean by that, we could then make it so that any contract, when it's updated, has to agree with the contract above it, which has to agree with it. So you get a chain of contracts which ultimately say you're not allowed to do things which say put, human slavery or something, whatever. You have to choose those high-level values, and different societies will choose different values. But once you've chosen those, I think you can make the whole system sort of consistent with it. But boy, there are a lot of details there. And I totally agree. Both on how do you do the infrastructure to make that work right, and also how do you make those top-level rules, and humanity has been struggling to figure out what are the best political systems, what are the best social systems. So there's potential for huge human flowering, but as you say, if totalitarian forces get in charge of all that, that's not going to be a good thing.
Is the bar for safety potentially too high with this approach? In normal engineering, we don't say that we have to have a guarantee for safety before we deploy some system. We talk about probabilities and risks in terms of probability. What we're asking for here is a guarantee of safety, but that's not really how the world normally functions. So is it unrealistic in that sense, or?
Well, I think it's going to be essential. I mean, normally, like if you're thinking about safety of an airplane, aircraft, boy, when they crash, when they have failures, that's not good for the aircraft. So they're quite concerned about safety. But you're right. It's mostly in the probabilistic sense. Oh, yeah. What's the probability a bird is going to hit this engine while another, that and the other thing. They don't have adversaries for the most part. There's no terrorist trying to, subvert the systems in general. Whereas military is all about adversaries. But they're human adversaries. And in fact, they're military human adversaries, which are kind of, clunky and so on. Cybersecurity, that's getting into much more sophisticated adversaries. And we're seeing huge numbers of break-ins. We've just had a thing where huge amounts of Las Vegas were shut down because of cybersecurity, and we have all kinds of blackmailing and all kinds of that stuff. Well, with AGI, I think we're going to have an adversary that is way beyond anything we've seen with human adversaries. Every single AGI will be as good at breaking into systems as the very best human hacker. Every single AGI will be able to solve intricate mathematical problems better than any human. And so I think we absolutely have to have the rigorous mathematical proof if we want to have a hope of. And AGI tomorrow is not going to be as powerful as AGI 2 years from now. And so, yeah, maybe we can make a system today that kind of works and it's fine for today's AGIs. But for the AGIs of 2 years from now, who knows? So I think if we want to be confident of our safety, we need to base it on the absolute guarantees.
Yeah, when we have these mathematical proofs of safety, this also means that no matter how creative an approach the AI takes, it can't do something that's provably impossible. And so we don't have to kind of plug the holes in our approach along the way, which is how you would normally do this in engineering, and I guess how other approaches to AI safety would have to kind of evolve with the threats along the way.
Exactly.
Many listeners, I think, will be interested in a proof of concept or a toy model or something that's a proof that this can actually work. Do we have something like that where we have a provably safe system in a limited domain?
We don't yet. We just put this paper out a few weeks ago.
Maybe it's too big of an ask. But maybe we have some precursors in that's not related to AI safety that proves that this could actually work in the real world.
Well, I mean, all of the pieces that they're improving the this and that have current precursors. None of them, I think, come together at the level it is here. So Max and I put in the end of the paper, we put a number of small little problems that I think are pretty doable with today's technology that would begin to build up to the big story.
So what are the most important research directions going from here? If people are interested in this approach, what are the most important problems to solve?
The core of all of this is theorem proving. And you actually could get around having AI theorem proving just by having humans prove those theorems. And probably the mathematical proof assistant, they call it, that's having the most excitement and interest right now is Lean. And it's based on something called dependent type theory, which is very beautiful and it quite naturally represents both computational ideas and mathematical ideas, but it's pretty sophisticated. It requires some real effort to read through the Lean documentation and to get in there and start proving theorems yourself. Nonetheless, I think they have 1 million lines of code now, and they've proven like 100,000 theorems, core theorems, and they're proving theorems right at the leading edge of mathematics. There's a mathematician who had a proof of something that was so complicated he couldn't keep the whole thing in his head at once. And he went to the Lean people and says, here's a test for you. I have this, I think it's called liquid tensors or something. I can't quite be sure my proof is absolutely right. Could you help me formalize it so we can check it? And a big group of people got around and they did it. And it's, a huge success, but it's still very human driven. They're gradually adding tools that make the machine able to do longer and longer steps in the proofs. So they're making it so it's easier and easier. And because it's such a building system and they have lots of human proven theorems that they can use as training data, Lean has become one of the main targets for AI theorem provers. And the most advanced one, I believe, is this hypertree proof search from Meta. But there's an open source one called Lean Dojo, where they have built up the tooling for AIs to find these theorems, and for the AI to make suggestions to you as a human mathematician trying to prove things. And they have open sourced a less powerful AI for doing theorems, and that's open source. And so I think that's a great place to start. And I would love to see. Right now, Lean is heavily weighted toward abstract mathematics. I would love to see more practical things getting in there. Certainly, software. Like I would love to see a Lean spec for like the C language and start doing verification of C programs and so similar hardware and so on. Actually, I saw somebody who was doing Lean models of voting systems and proving properties of voting systems. So it's like, yeah, let's get some social science in there, some economics in there. So that feels like it's got real momentum. And they just released Lean 4, which is an incompatible upgrade from their previous ones. And they just translated their whole mathematical library into Lean 4. So it feels like it's right at the place where textbooks can come out and people can start using it and really moving it forward. And boy, I think there's huge number of PhD theses available for, do AI safety using Lean and verify it and so on. So there's that whole thing would be great. The other piece is I think the hardware is really, really critical. And secure enclaves, like Apple has that. Intel has their own secure chips, as does all the different chip makers are starting to have the equivalent of secure enclaves. But I don't think they're quite doing the level of tamper sensitivity that we need if we really, really want to be guaranteed sure against a powerful AGI with robots and all that kind of stuff.
Could you explain that actually? How can a piece of hardware become more tamper-proof? It can't look at itself in simple terms, right? Unless you have some sensors, of course. How does it know, so to speak, that it's being tampered with?
You need the sensors. Well, so there are several ways to attack a cryptographic chip. One is to break the cryptography, and that's what the cryptographers focus on. But that's not how most things, or that's not the easiest way to break things. What they often do is they look for side channels. So, and some of those are completely ridiculous. Like, in the normal world, we use passwords, which you type in on your keyboard. Well, it turns out the sound of you typing, there's now a deep learning model that can listen to you typing and figure out what your password is. And it doesn't even have to be in the room. It can use the microphone on your cell phone, or it can bounce an infrared laser off your window pane and get the vibrations of your window pane, and then use that to figure it out. So the side channels really bad. Or another one, just to say, because it's funny, is the power light on your computer flickers with the power usage, and as a cryptographic algorithm is decrypt using a key, the power light blinks. And from 100 yards away, somebody was able to have their, a telescope looking at this light and reconstruct the password from that.
I think you just made me significantly more paranoid about IT safety.
Well, it just shows that we haven't been thinking about it, right? And we haven't been thinking about adversaries that are really using all the channels available to them. So how do we do that? Well, first of all, we need shielding, right? So you don't want signals leaving your chip. And so that's pretty easy to do. You can make a Faraday cage around it and so on. The harder one is really advanced attackers will, use acid to etch the top of a chip off. And then they can use scanning electron microscopes to try and, find the charge on the chip and read secret information that it shouldn't be accessible to them. So we need to protect against that. And I think, given sufficient energy and money and so on, you can break into anything. It's hardware, you can blow it up, worst case. So I think the zeroization idea, which is, you can break into this thing, but you're not going to get anything that's of value to you. I think that's fundamental to this. And so that means you have to absolutely be sure you can sense when the chip is being broken into. And so there are, mechanical sensors, like, you have sort of a protective membrane around it that if it's punctured, maybe you have, an LED light, and if light gets in the wrong place, that triggers. And then that can delete all the keys. And so you want to make sure that deletion is very reliable. And so that means it probably has to have its own little battery there. In general, you don't want your power directly powering the circuit that's doing cryptographic stuff, because then signals can go out the power line. A better way is you have like a little battery or a capacitor that actually runs the chip, and then periodically it stops everything and recharges it, from outside power. So techniques like that. And I would love to see a formal proof based on the physics of everything. So just like cryptography has made great advances by having formal, precise mathematical models of their assumptions about attackers and eavesdroppers and so on, and then proving different properties. I think we need the same thing for hardware. And the great thing about hardware is if you can really make a little unit, a little processor that is absolutely guaranteed hardened, then almost all the problems of cryptography go away. We can do it all with really highly secured hardware. And so, but that's a whole discipline that needs to be developed. And fortunately, there are groups doing, like the Secure Enclave and Apple and so on. But I think they need to go to the next level. Oh, and let me just mention one other. You can extend zeroization just from bits. I think you can extend it to physical actions too. So like, let's say you're making some dangerous pathogen in a little enclosed lab or something, and now you get sensing that somebody's breaking into that lab. Well, what should you do? Well, you should destroy that pathogen, right? You're going to lose your work, but at least the bad guy is not going to get it. So every, chemical synthesis should have, acid, a little acid container there that under the right conditions, destroys the acid. Or a robot arm should have little fuses inside its motors so that if somebody tries to take over that robot, it blows the fuses and the motors don't work anymore. And so it's a way of preventing attacks from taking over equipment.
This issue of cybersecurity and hardware security, it's one of the few areas in which the incentives are pretty much aligned between major AGI corporations and people who are within those organizations and outside those organizations who are very interested in AI safety. So I think it's in the interest of OpenAI and DeepMind and Anthropic and so on to secure their models and to not have break-ins either via the internet or via hardware.
Yeah, that's a really great point. They should be totally aligned with that. And so maybe that can be pushed ahead really quickly. And a lot of non-AI related things need that too. I keep hearing of just ridiculous break-ins. I think the train system in Poland had no encryption on the control of the trains, and some teenagers were able to get in there and start, controlling the trains. Woohoo, party!
That's funny until it's very dangerous.
Totally. Could kill millions of people. And apparently satellites had no encryption either in the control signals. And they just thought, well, nobody would have access to that band. It's probably fine. So we haven't been in the security mindset much in recent years.
Okay, I think we've sketched out an overview of the approach that you and Max take in the paper. I want to go through some of the applications, and I think, if I'm right, these should be seen as parts of a whole. This isn't a complete solution, but these are pretty interesting ideas for how we might apply all of this that we've been talking about. The first of them is mortal AI.
The mortal idea is an AI which isn't gonna. So today's AI is a program which runs on some hardware, and as long as you got the hardware and you got the power, it'll run forever, right? If your hardware doesn't go bad. Well, that can be pretty bad, and it may be that you want to do one thing and then be done with it. And so, wouldn't it be great to have hardware where, after a certain time, say 1 year, it's guaranteed to stop and maybe even delete the program, and so that gives you some form of control over an AI.
And a bit along the same lines, you have throttled AI. What is throttled AI?
The problems that are emerging are AIs which are require huge amounts of compute. I think the rumor was that GPT-4 used like $100 million worth of compute, something like that. And we have these vast data centers. I'm just reading. So the H100 is NVIDIA's amazing chip that seems to be better than all the competitors. And I've heard they're selling a million H100s this year. So that's a huge amount of compute that's getting created there. And so, one of the pathways to risk is people training huge models on these huge data centers with no controls on it. And so maybe it would be good to only give limited computation power to these systems, and maybe have some regulatory body in charge of how much that should be. But how do you do that? What if somebody gets some GPUs in their basement and they're running it? Well, maybe we should have the chips themselves, the H100s or the future H100s, have a mechanism for only running computations if they have a token which says that this is validated, this is an okay thing to run. I think this idea originally came from Anthony Aguirre, and you could drip those tokens out in a limited way. And if somebody, was not obeying safety regulations, you just don't give them any more tokens. And if the tokens expire in a short time period, that's a way of controlling or limiting how much compute is available.
Although, doesn't that make you a target? So doesn't this incentivize the AI to deceive you or capture you in some way where it can get more of these tokens? It might incentivize the AI in the wrong way.
Yeah, totally. In fact, that's a really important point, that all of these things which attempt to limit AIs in one way or another create incentives to break those limits. And so that's why things need to be super, super hardened.
This is maybe a bit of the same problem as if you have an AI and it takes an action, and the way you control it is to say, okay, did you like that action, right? It's now incentivized to manipulate you, or maybe subtly in a way that you can't understand, so that you click, yes, this was a good action.
I read that the red teaming found that the more powerful the models are, the more they try and tell you what you want to hear rather than what's actually true.
The red teaming of which models? GPT-4 or?
I think it was the GPT-4 red teaming team. Yeah. And they did a really nice paper, Archival's group, which did that. And they found that it becomes more trying to tell you what you want to hear as it gets smarter because it's figuring out that you want to hear that.
One last potential application here is the least privilege guarantee. What is that, and how could that be useful?
Well, so in complex systems or companies, which are dealing with important and secure information, this is a principle which is often used. You don't want everybody in the whole organization to know everything. And so you really want to give each participant the smallest amount of information they need to do whatever they're supposed to do. And that increases the overall sort of security of the complete company. Apparently, Steve Jobs was really into this. And in Apple, like apparently the people that worked on the very first iPhone, many of them didn't even know what the product was going to be. And so from a human point of view, I find that kind of, man, that doesn't seem like it would be very fun. But it was very effective at keeping it secret until they launched. And, you know, that company is notoriously famous for being able to keep their internal stuff fairly secret for critical, military, political things running on AGI. Having AGIs not having the whole story may contribute to safety properties. How do you do that? Well, we need some kind of control mechanism to ensure that information is only going to where it needs to be. And so that's just another mini constraint that might be interesting to see how to implement.
In a less important application of this least privilege guarantee, you could imagine having your AI assistant in the potentially pretty near future. And then you want to say, okay, I have a lot of information on my smartphone. I have my health records. I have my banking information. Maybe I want my AI assistant to have access to my calendar, but not my medical records and my banking information. And so that must be the way it's done. Otherwise, I think people wouldn't be able to trust these systems. But yeah, I could see how that's useful.
I find I use Google Drive, which I love. It's a really great system. But if you want to use apps on there, they say, oh, you have to give this app some permission. And let's say you want to edit an image. So you download an image editing app. The little box says, this app will now have access to your Google Drive. It's like, what? I wanted access to this image and nothing else. And hopefully that's what it does, but it doesn't really communicate that in a way that I'm sure, you know?
In the beginning, we talked about basic AI drives and self-improving AI. And you published on this how many years ago now?
2008, something like that.
What are these basic AI drives? We've kind of alluded to it throughout this conversation, but maybe sketch out the case for why AIs would develop basic drives.
So this is a case where an AI has some goals that it's trying to achieve, and it's improving itself. It's able to envision the implications of taking certain actions, and it's trying to achieve those goals. And so in the papers, I like to use a chess player, that this AI's one and only goal is to play good games of chess. And so that seems harmless. It seems like, okay, great, a little chess playing. What could possibly be wrong with that? And the problem is if the system is truly goal-driven, and goal-driven in the sense of it figures out which actions will best lead to its goals, and it takes them, and it has knowledge of the world, as our current AIs, very rapidly do, then it actually leads to all kinds of dangerous sub-goals. In particular, as it's trying to, learn to play better chess, it realizes that, if I had more compute power, that would really make my chess playing better. How can I get more compute power? Oh, well, other people have compute power. Oh, if I can break into their computers, then I can play better chess. Great. So they go breaks into other computers. Or let's say, it says, all right, even better, if I could buy more computers, that would be good. Oh, I need this thing called money. Well, where's money? Oh, money's in banks. Oh, if I can break into the bank, that would be great. I can get more computers. So it's now incentivized to become a robber or a thief. If somebody, says, well, I don't like what you're doing, you're breaking into banks, I'm going to unplug you. If they are unplugged, they're not playing any chess. They no longer meet their goals. So the chess playing goal leads to keeping yourself from being unplugged. If the person persists, well, then they say, oh, this agent wants to unplug me. That's totally against my goal of chess. I better stop them. stopping them, however, it may lead to murder. And so we get a whole range, and we flesh out a lot of those in there, of these goals that really don't depend on chess. And so lately they've been called the instrumental sub-goals, that they are things which help enable other goals and which arise pretty much from any top-level goal. And so that makes them kind of dangerous. And we can see their analog in biology, where, organisms do try and take resources from other organisms, and they do try and keep themselves from being killed, and so on and so on. Humanity, one of humanity's great strengths is we still have those, right? We have, sort of sociopathic instincts and so on, but we also have created this amazing culture that supports cooperative interaction. And so those, push against those sort of basic underlying drives. We've seen in today's AI models, every single one of these drives has shown up, in like game-playing agents and so on, but in pretty muted forms. Fortunately, we don't have any actual real powerful agents roaming the world at the moment, though it's kind of shocking when the large language models came out. Hundreds of projects to turn them into agents showed up. So here's a large language model. Let's give it a goal and let's have it search for ways to achieve its goal. And the worst of those was something called Chaos GPT, where somebody anonymous set some GPT-like model with the goal of destroy humanity and saw what it did. And then he made videos of what it did. The best way to destroy humanity is to blow up nukes. How do I get nukes? Let me go look that up. And sort of showed its whole behavior as it tried to do it. Fortunately, I don't think it's smart enough to actually do anything, but watching its thought process was terrifying. And I think that video, he also had a Twitter channel, which I think is gone, but I think that video is still there. And you can see, oh my God, if that thing had power, this would be a really horrible entity to be in the universe. So I think it's something to really be worried about. And that's one of the reasons I think I was so excited by this provably safe approach, because that's the one and only mechanism I've seen which could rein in the behavior of even that kind of bad agent.
Do you think that AIs will become more like agents in the future?
I don't think it's good for humanity to have them being agents. I think there is a tendency for them to become agents. I don't really know if we can make limited agents. I mean, it's funny to look at large language models. I was, at first I thought, all they do is predict the next word. They can't possibly be agents. They have no goal. What is it, And yet they often act very agentically. And so the model I kind of like now is they're trying to mimic what's on the internet. And what's on the internet is the output of many, many, many agents, all humans, and maybe some other entities as well. And they have learned, if they've learned well, they can learn to mimic agents. And as you give them different prompts, the agent that they mimic gets changed. And there's this whole thing called the Waluigi effect, which is whenever they mimic a good agent, there's often a bad deceptive agent underneath it that it's also mimicking, and that bad agent can come out with the right prompt. And so somebody's trying to explain why Bing Chat got so crazy and bonkers. And so I think agency, it's something which has emerged multiple times in biology. And so I think it's a natural process. I think it's pretty risky for us. And so I don't quite know how we should balance that. It'd be great if we could keep them as tools, but I'm not sure that's going to be possible.
Do you think agency and perhaps also a model of the world is an emergent property of large language models? Could the next GPT-8 or whatever it is develop agency in a way where it's not an explicit goal to create agency?
Yeah, well, let me start with the world models. Years and years and years ago, I used to think about the thought experiment of if you just listen to the radio all day and that's your only input, could you learn about the world? Could you learn anything about the world? And at that time, I thought, no way, you're just hearing little frequencies up and down. But then I thought, well, if you watch TV all day, well, then maybe you could really learn about the world, because you could see the regularities and the patterns in the image, and you'd learn about three-dimensional geometry, then you'd learn about physics, and then you'd connect that with the voice that people are saying, and you'd learn about humans. And so you could pretty much learn everything, I think, by watching a video signal. I think I've been proven wrong that just from the regularities of a sound signal, just listening to the radio, and just the only task being predict the next little signal, the best way to do that is to build a model of whatever is creating that signal. And so You can quickly learn about phonemes and sounds of the world and so on. And then you quickly learn about the grammatical structure of language. And then by the patterns, you start building up a world model. And when GPT-2 or something, people started showing GPT-2 knows where the cities on Earth are. So like if you say you're in, Berlin and you go 100 miles south, where are you? It knows. It's just like, holy crap. It's created like a 3D model of Earth from just people talking about stuff. And now that's been taken way, way further to where the current language models, I think, have very, very detailed and good world models. They have inconsistencies in them, which is part of the flaw, I think, in the current models. But if you sort of train them to make them self-consistent, I think that's where you go from a kind of fuzzy world model to a really precise world model. And so I think that's inevitable. The agency thing, I think they can mimic agents. So there's your own agency. Yes, I want to do that. There's also understanding other agents. Sometimes they call that theory of mind. That and they already, the larger language models have pretty good theory of mind. You can, say, Fred put his candy in a box and then he left the room and Sally took the candy out of the box, but Fred came back in. What does Fred think's in the box? And so it keeps track of what's really in the box and what Fred thinks is in the box. And they can do that.
Yeah, and you can track the development of large language models' ability to model other agents' mental states evolving over time. So GPT-2 might correspond to a 2-year-old, GPT-3 to a 4-year-old, GPT-4 to a 9-year-old. Those are not exact numbers, but you can see how theory of mind develops in these models. It's pretty fascinating.
Amazing.
There's some research where you ask a language model to play chess against you just using text, and you can see that it develops an internal representation of the chessboard, which is at least some proof that there's some model being generated. And we might imagine that this extends to modeling the physical world or modeling people or anything, basically.
Some shocking stuff that came out just a few weeks ago. Apparently, I think it's GPT-3 or GPT-4, one of those. If you just try and tell it to play chess with you, it can play chess, and it has like a rating of 1800. It's like, I can't in a million years imagine, because chess, I think, requires searching and stuff that I don't think language models do very well. And yet, apparently, and like you say, I think somebody did experiments on Othello, which is a simpler game, and they were able to find, they did mechanistic interpretability they trained a transformer on Othello, and they were able to find the board representation in it. And so in that one, it really clearly, just by looking at games, text descriptions of games, it clearly created a board, and it could know what the state changes were and so on. So that's kind of magical. I wouldn't have guessed that a priori.
Yeah, one of the concepts you wrote about, maybe again 15 years ago, is this concept of self-improving AI. The original vision of how this would happen was an AI might quite quickly, over a time span of maybe some months or days or even hours, begin to self-improve. Do you think that's still in the cards? How has this concept of self-improving AI held up?
I don't think they're doing it automatically that I have seen, but certainly people are using them. Like the H100 that NVIDIA, their biggest chip, I think they have 40,000 subcircuits which were designed by AI running on NVIDIA chips. So that's, a little bit of a distance. And for a while, Google was a real champion of what they called AutoML, which is using AI systems to tune the parameters, how many neurons, what layers, what learning rate, what learning algorithm, all that stuff. And they were optimizing it and getting, much better performing neural nets out of it. And that looked like maybe 3 or 4 years ago, that looked like the hot thing, that everything was going to go that way. Doesn't seem to have happened. You don't see many people talking about it. Instead, everything's getting sucked into transformers. So transformers, first they did text, now they're doing vision. GPT-4 just got a vision part, and Twitter is full of people doing just mind-boggling stuff with that. I think they're also generating images. So they've integrated DALL-E. They have DALL-E 3. I think that's integrated with GPT. They're doing audio, eventually tactile, and robotics. So it seems like everything is kind of getting pushed into the transformer. The transformer model seems to be rich enough to deal with any modality. Doesn't seem very efficient. Seems like an incredibly inefficient mechanism to me. And yet that doesn't seem to really matter. So maybe maybe we'll have systems which will redesign themselves. They'll learn everything in the transformer, and then they'll make a much, much more efficient representation for particular tasks or something like that.
As you mentioned, self-improving AI, in some sense, it's happening, but it's happening through humans right now. So you might have engineers at the top AGI corporations having an AI help them draft some piece of code before they check it through and implement it. But do you think we could see AI more directly intervene on its own code or create its own hardware in a more direct way?
Well, so today, assuming we stay on this trajectory of using transformers or some other universal model, you can try and improve the transformer. There are a bunch of variants, like I think hundreds and hundreds of variants of transformers, which are more efficient in one way or another. And yet, remarkably, almost all the big models seem to be using pretty much the standard transformer. You can create your own training set, and that's the synthetic data story. And I think that really kicks in once you can, with theorem proving, once you can check generated data. And then I think you're going to see models who want to know more about something. They've learned everything that humans know about it. Okay, let me go explore, generate a whole bunch of examples, do searches, find solutions, and then train on that and figure out which concepts are the most important. I think my current sense of how it's going to happen, how self-improvement will generally happen, is within a fixed architecture, and it's changing the ontology, if you like, figuring out what new concepts are important in order to explore a certain direction. But I don't really know. I mean, it could be, we're in this weird phase where there's like kind of universal agreement. Everybody wants H100s, and there's a black market of H100s, which are 3 times as much as NVIDIA sells them for, and they're sneaking across the border, and that's this is the way to do it. Transformers on H100s. Maybe this is a temporary thing, or maybe this goes off into I think it is possible that technology scaled up will get us to AGI. Whether it's the most efficient way to get there isn't really clear to me.
Easy question for you. How far do you think we are from AGI? How far are we from AI that's as capable or maybe more capable than humans across a very broad number of tasks?
Well, so I'm not really a great prognosticator, but I follow Metaculus. Metaculus is a prediction market where a bunch of people come in and they bet on things like that. And they have 2 on there right now about AGI. One is kind of a weak AGI. One does something which is as good as a human for things where you're interacting over the internet. And that's the weak AGI. And they're saying 4 years right now for that. And then the strong one is more like a robot interacting in the world physically. And that one, they're saying 8 years. So either way, they're pretty damn short. And then you see guys like Dario Amati, head of Anthropic. He just did an interview where he said, AGI in 2 to 3 years, I would say. So, and those guys are in a position to really know. On the other hand, and then the question is, once you have AGI, how long to get to ASI, artificial superintelligence? And on Metaculus, it's 8 months after that. I'm not sure that question is really the right question, though I think it is related to it. I mean, the right question is, how long until AI starts being a serious risk or factor in human affairs? I mean, that's the really critical question. And on the one hand, I don't think you need to be human level in everything to do that. Today's AIs may be good enough at, playing the stock market or something to have a big impact on the stock market. On the other hand, it may be just if you're as good as humans, maybe that's not impactful. What would another human be? Big deal. Except you can make many, many copies of them. So now you can have 1 million humans, and that starts getting a little scary. And then once you get ASI, then you can have huge, huge impact. So I think that those 2 questions are very related. My sense is that the AGI is probably within the next decade, and the large impact could happen on that scale, or maybe a little longer. But I would say not more than a few decades, probably.
It's interesting how quickly the kind of general consensus around these timelines to AGI have changed, because it's almost as if now the thinking is that we might get to human competitive AI within 1 or 2 decades. And that wasn't the consensus, 20 years ago, far from it.
Oh, yeah. Many thought it would never come.
Exactly. Well, I spoke to Robin Hanson on this podcast, who's been worked in AI and kind of, have a lot of experience with AI over a number of decades. And he remains skeptical I wonder if, I mean, you've also been engaged with AI for a long time now. I wonder if you perceive a certain hype in the zeitgeist at the moment, or do you think this time is different? This time it's for real.
Well, it's really fascinating to look at the history of AI because it's had these huge swings up and down. They call them the AI winters and the AI springs. And it's really funny. Frank Rosenblatt invented the first neural net. It was actually the first neuron called the perceptron. And I think it was 1959, something like that. And he had this elaborate, complicated thing with this neuron with wires all over the place. And he was blasted all over New York Times, this and that. And they had quotes saying, this is Frank Rosenblatt, and this perceptron is going to be the thing that walks, talks, has consciousness, and changes our society. That was like 1960. And at the original AI meeting in Dartmouth, where it all got put together, they did a summer school. Yeah, over the summer, we think we can do this AI problem, and I'm going to have a grad student do vision next summer, And so they had these really short timelines. And then, like in the 1970s, it flipped the other way. There was this brilliant physicist named Lighthill, loved his books and everything, but he came out in Britain and he said, this field is hogwash. They haven't done a single thing. All money should be completely shut down for this. It's garbage, And so I was like, what? And so we get these ups and downs because I think it's so, the implications are so big. I think people's thinking either, explodes or shrinks. And so we could be in a period of hype, though, like, I don't know if you've seen the Microsoft commentary. There were a big, long Sparks of AGI paper about GPT-4.
Yeah, I read it, and it's extremely impressive. Some of these things were not even, I think, the final release of GPT-4, but a precursor to GPT-4 is explaining very high-level mathematics and just kind of many examples of seriously impressive things there.
So it seems to me that model may already be sufficient for full world transformation if they got the lying and the reasoning tuned up a bit. And so, for better or worse, it feels like we're right here. And I don't know if you've been watching over the past week, Twitter's been full of rumors that internally OpenAI has AGI. AGI has succeeded. And then Sam Altman came out and he tweeted, yes, we have AGI. And of course, I would announce that on a tweet.
I think this is a sign that people are nervous or people are excited. There's a lot of the atmosphere is tense surrounding this subject. But what we want to do is kind of keep our heads cool about it and try to remain calm. Even though, as you say, there are people who are good at forecasting these things arriving pretty quickly. And so it's difficult to know whether the right attitude is to remain calm or to work on nothing else.
Well, I think we should take a cautionary approach, that we should, assume it might arrive in 10 years or sooner. What do we need to do to make sure that is not catastrophic?
And that's what you and Max are trying to do in Provably Safe Systems.
Exactly. Yep.
Steve, thanks for coming on the podcast. It's been a real pleasure. I've learned a lot.
Great. Thank you so much.